Yeah, so today's talk is going to be functionally designed application and making it transparent. Before anything, thanks John Digos for anything and everything, for building up such a wonderful community. Thanks Adam for not sleeping ever. Thanks for replying to my messages instantly, regardless of what time it is in US. Thanks a lot for supporting writing this application for our client. Thanks Sandra for organizing this event. And thanks everyone at Ziverge, who are my colleagues and all the sponsors. What to expect in this talk? An example of a functional design code base and why we did that. And then a bit on attribute grammar, not talking specifically about the attribute grammar, but more about recursion scheme. That said, this is not an introduction to functional design and recursion scheme, etc. There is great talks from different people, especially John Digos' course on introduction to functional design. There are so many talks on recursion scheme. And obviously we expect some level of familiarity with Zio ecosystem, because I'll be showing some Zio types and I may be missing explaining why I'm using that. And another heads up is I realize that the code, it's a code in 10 slides. Most of the slides are just code and it can be a little bit annoying. So it's a excuse and it's intended for future reference. I want these slides to be available and people to come back to these slides and refer to these implementations when you're trying it out by yourself. And all these concepts are backed by different blogs and papers and talks, which I'll be listing down towards the end of the talk. A little bit about the history of why we are building this. So this is for one of our clients. And the history is the platform that they are running their queries and their applications. They want that to be observable. And in order to make it observable, they built a thing called as metric service. It's a backend service. Consider that the name metric to be anything, right? In your case, it might be a customer attribute or an attribute of any entity that you're trying to query for. So in this case, we are querying for a metric from this service. And these metrics or attributes or features, whatever you call, it exists in various shapes and different data sources at various time intervals. And the key thing is, or the key problem is, it takes weeks or even a month or even more to bring a new metrics in production. And the main issue with that is dealing with the code, which is not quite transparent, which is hard to debug. So to sum up, that's a code which exists in our client side to make things observable for their platform is not observable. And as I mentioned, the metrics can be customer attributes, or it could be anything, right? You can query for anything. All that matters is the abstractions that we built, and the details are secondary. Okay, to repeat some of these specific problems, I just wanted to reiterate through the problem statement. Data for a feature or a metric or an attribute can exist in multiple sources at different time intervals. And we need to collate all these results from various sources, or we might need to, try one data source, and if not, try the next data source and get the one that wins. And plus optimization, I'm not sure if I'm able to go through how we can do optimizations on abstractions. I had to take off some of those information because I was running out of time when I was practicing it. The key thing is transparency. And the key thing is making your code less opaque, making your code and whatever that is happening inside the code really transparent to the developers. If the developers are not productive, the business is never going to get productive output. And track the performance. We'll come back to that. Anyway, this is actually a common problem. And I thought it's a good idea to give some idea of what we are trying to do. And maybe it is applicable to most of the use cases dealt in various companies. So we started with a specific problem, and that problem is actually the same, or it exists in different shapes, but almost quite similar to each other. And it's quite common in our industry. So what's the solution to all of this? I kept mentioning about transparency and observability of your code base. What is this all about? The solution to that is an execution plan. Like if you're familiar with frameworks such as Spark or Flink, you have this execution plan that that provides the information of what this is going to be done. Like what are the stuff that is going to be done by the application. So you have a vision to that. But then it's just not enough to have a plan. You need to have a summary. And with this talk, my point is the summary is essentially the plan itself, plus some extra details. So the shape or the generic shape is the same. So to begin with, as a solution, we represent the fact that our metric or attribute is a DSL. And that can come from a data source. So we have a source node. And that can be a ratio metric because it can be a ratio of one metric to the other. Or it could be a sum of two metrics. And it could be an oral logic, like you try one metric and you try the next metric if the first one fails, right? So this metric can be a metric in data source 1 or else a metric in data source 2. And we are happy with either of them. And then we have this within node that points to this problem of time ranges. Like, okay, one attribute or a metric is available in a data source for one particular time range. And if not, like the user is asking for some other time range, so probably it's a better idea to go into the next data source where we have the metric available for that time range, where time range is represented by a abstraction, which is called as relative time, essentially making it easier for us to play with this metric DSL without having to worry about any Java instance or durations. And the data source itself, which was available in the source node, it can be an empty data source, or it could be a AWS S3, or it could be a Postgres, which holds the information of what query needs to be run against this data source, against a Postgres, or it could be an in-memory cache. So cache itself is another source for us. I know I have been throwing some abstractions at you, and I may not be going into the subtle details about it, and that is intentional. It's just about giving you a gist of what a functionally designed code is going to look like. And why are we going through this pathway? We will end up in an abstraction that is super important for us, but before that, I'm just giving you some idea. So this is the primitive side, right? So my metric is a source of Aurora with some expression logic. We have our own Expert language, which is very lightweight, which is geared to solve the client's problems, which then get converted to a SQL query, which you can run against the Postgres. That constraint is going to give us a lot of flexibility. Or it could be from S3. So we have these two primitives going in. And S3 can be just consider that as an API endpoint exposed somewhere, so you can hit that service and get the result. So if you want to know how this is going to look like in order to define a new metric or an attribute or a customer feature in your analytics engine, well, this is quite simple, right? Those subtle details are part of the original definition itself. So you don't need to look at any other part of the code on what's going on. My customer attribute is this kind of an expression, some kind of a constrained query language within now and last 6 hours. So for the last 6 hours, this is going to be in Postgres. If the customer is asking, if the user is asking for a metric in the last 6 hours, that's going to hit Postgres, or else it's going to hit S3 from the beginning of the time before 6 hours to before 6 hours. Yeah. So internally, we can do a lot of things. One example is add in-memory cache data source into the original definition of the attribute. So when you give this updated metric to our interpretations or implementation layers, it's going to first hit the memory cache. If that's not available in the cache, then it's going to hit these data sources based on the definition that you have provided. So what's the end-to-end flow? We've seen some abstractions. Okay, sure, got some vague idea. So what's the end-to-end flow? So you got this request. Again, this could be any request, right? That's the input request. Can come from a GraphQL endpoint. It could be something that you're trying to query from your local machine or whatever. That request is mapped to the metric DSL that we have just written. Okay, you're asking for some metric of the type A, and that can be mapped to the DSL that I have provided in the analytics engine. And then that metric gets converted to the final result, which is now represented as a Z stream. As I mentioned, I hope you're completely familiar with this beautiful Z stream. But that's not the end-to-end flow. There are more abstractions in place. And one of those abstractions is called as query. This represents a physical query that runs against these data sources, right? So we have already got a couple of abstractions. Now this is a third abstraction that represents a physical query. So if it's from the cache, this is a query that represents hitting the cache. Or if it's from S3, that's a node that represents hitting S3. Or if it's actually a query that runs against a Postgres, that's a SQL query, which in turn has another set of ADTs. So in this talk, we are not going to explain how an expert is converted to a SQL query and so on and so forth. They can be boring details. But essentially, you can imagine the ADT that represents a SQL query consists of select, from, filter, group by, and inner join. Okay, so what's the end-to-end flow now? It's going from request to metric, and maybe metric can be converted to a query, and a query can be converted to an Z stream. Close enough, but it's just not enough, because query has all the power that metric DSL had. So we had a sum metric, right? We need to run one metric, and we need to run another metric, and we need to sum all of that. How can that be represented within the query? You could represent within the query as another ADT, but that's that is not making things orthogonal. So we are going to have the most important, the heart of our application, which is ops. And ops is polymorphic with respect to query. So is usually representing a query, basically representing the actions that needs to be taken after running every query. So I need to run a query that's going to give me some result, and I need to sum all of those queries. So in this case, sum is a non-empty chunk, again, coming from zero of ops. So the result of all of those operations are taken, and then we sum those results using an execution strategy. And this is where this abstraction is going to be useful. Right? This is very closer to the interpretation layer. It's very closer to the implementation layer, that you have so much of information embedded into this ADT, unlike the metric DSL. You might be thinking that this is very close to the metric DSL, but it's something that is representing very closer to your implementation layer. And I realized that this abstraction can be in place in many, many applications. So from now on, we'll be focusing on this layer. Okay, so this is our end-to-end flow. A request is converted to a metric. It's not really converting. You're mapping that request to a metric DSL. If you have a metric DSL that represented our customer feature, you can convert that to an execution plan. So the first problem is almost done there. So the execution plan is ops of a query A, a query representing some data that's returned and its type is A. And that ops of query of A is converted to an ops of a Z stream, which is quite straightforward, because if you know how to go from a query to a Z stream, obviously you can go from ops to an ops of a Z stream. It's easier to have a map in ops. And then once you have ops of a Z stream, you can fold over based on the different nodes in ops, like sum of to Z stream. Yeah, I think I have some semantics to it, and that gets folded over to the final Z stream. And that thing is so familiar to many people, especially those who are familiar with recursion schemes. We're not going to talk about recursion scheme straight away, but that's like giving you a hint where this is going. So, okay, we will get the plan. So how do we get the plan? This is an example, right? If you have a request that is going to hold the metric DSL information, and then the first node is a within metric, like within node. So if you are asking for a customer attribute for a particular time window, that's a requested time window, but then the within node will have another information saying that, hey, that metric is available only from start to end. So that's the available time window. Then you can match versus you can have an if else condition where if the requested window is a subset of available window, well, that's cool enough, right? We've got the results for you ready. Basically call the plan again with the loop. Remember that metric within is recursive. And if it's not available, it's a failure. And if it's available, but only a part of the time window is available, then it's a partial result. All of that is being dealt in the ops node, in the ops ADT. And then it goes back into the next loop, and then it hits the orals condition. And if the orals condition has left and right, and you call the plan for the left and call the plan for the right, and if both of them returns a partial result, then you match the window. If it is forming the actual requested window, then I can then pass the union. And if not, I can just fall back. Actually, that implies, okay, ops 1 and ops 2 can give your metric, so you need to try one of them. Again, this is just giving you getting a gist of this is enough for now. Anyway, so metric was data. Metric DSL was data. So the execution plan, which is ops of a query, was a data too. So it can be pretty printed. Obviously, the ASD that I have chosen to go from the execution plan to something readable is JSON. I use ZeoJSON for this, basically converting your ops to ZeoJSON. So the leaf node will hold the A, and if you know how to go from A to JSON, you can convert a plan. Again, keep a note that it's not specific to a query. It can be ops of anything, and you can pretty print all of that. And this is an example of a query plan or an execution plan. It says it's a union of 2 fallback operations, of which first fallback says I need to hit the cache, and if that is not there in the cache, then it's going to hit the database, and then union that result with the next fallback operation that is again requesting the cache for some other metric, if not a sum of 2 other API calls. And then union those results. So we know exactly what this application is doing. Yeah. And this is like a concrete example of how this is looking like in our client place. We are using GraphQL endpoint. Not a big deal to go through that. In fact, I'm running out of time. So we need to convert this plan to something real. So if I know how to go from a query to an Z stream, I can compile the plan to the final Z stream. As you can imagine, you can pattern match on the ops node, and then recursively call the compile on the left and right for nodes like sum and or else. And this plus is available like in different name in the Z stream. And again, there are details. We can see that some node is taking care of the execution strategy. Again, that is also coming from Zeo. A lot of things comes from Zeo for free. So where are we now? So we dealt with a lot of abstractions. That was a quick deep dive. So we're done with the execution plan. Now what to do? We need to come up with an execution summary. So to repeat something that I have mentioned in the beginning of the talk, summary is plan plus something. So we've already got half of it. So when and why did it hit a data source? Like as part of the plan here, hitting various data sources, and that's the most important point. Many times, the answer to that question is make the stack of operations that led to that leaf node, which is ops.noop, available at the leaf node. So you're literally converting an ops of A to an ops of a history of things or a trace of things that led to the leaf node and the original value that is available in the leaf node. Yeah, and so this is a simple solution to that, right? So our trace is a list of ops. I always get scared when I give that, but it works. So trace is a list of ops, and query implementation, instead of going from query of A to Z stream, it's going to go from query A and a trace to Z stream. So this was our original compile. So we are adding more information into that compile based on which is trace. So at every node, you add some stuff into the trace, and you got it at the leaf node. At the leaf node, you then call this function, which is a query and the trace. That query implementation is query trace to Z string. That was easy. And if that's the only thing that we need to do, well, that's it. Like we don't need to go anything fancier from here. But we might need more information, such as I need a depth of each leaf as well, maybe to point out the fact that, hey, your application failed exactly at this particular node. So you need to have some sort of position or a depth of that leaf. Okay, that's also simple, maybe simple, may not be simple, depends on the team. Okay, that compile function is having more thing in it, which is depth information. Okay, but what if I have to have the access to the the result of subcomputations. Like we are doing ratios, sum, difference, and many things. And I need the result of each of these subcomputation, and I also need the final result too. So keep adding things into that compile, one single compile. We can have only one compile because you cannot run this multiple times to add more information. Like you're literally hitting the data source duplicate. So subcomputation will have this map. That may be or may not be, it works. It depends again. And the next question is, I need to also add performance of each of these subcomputations, not just the result, I need the performance too. And some of them are top-down logic and some of them are bottom-up logic in the recursion. And how can I map all of these maps into the original plan with extra details? And all of this is going to be tricky questions. So the first thing that I tried is, let's don't pollute the original implementation. And again, as I speak, this is not in the client side yet. And in fact, these code that I have written here is more geared for this particular talk. The first part is there at our client side. Again, let's don't pollute our original implementations. Let's don't pollute our compile method again and again whenever we have more requirements. That is not modular approach. So let's begin recursion scheme. And it's not going to be an intro. I hope most of you are familiar with recursion scheme. If you're not familiar, it's a good thing in your backlog to learn. So the building blocks, fixed type, the very first chapter 1 of recursion scheme, or maybe chapter 2. So fix represents a recursive structure that allows your recursive structure to be non-recursive. We'll see what that means. So this was our recursive structure, which is ops. And you can see left and right as recursive. This is also a simplified version of our ops that we have seen. We are converting that ops F to, we are converting ops to ops F. And we have a new type parameter B representing the recursion holes. And the original A will be there just as before. So this can easily have an instance of a bifunctor, because you need to be able to map both the A and B, of which you need to map B for recursion scheme morphisms. So type ops is the original ops. Recursive ops is basically fix of non-recursive ops F. So we've got the original ops back. And the basics of recursion schemes, especially on the folding side, we have got kata, para, histo. Kata represents if you know how to go from your non-recursive structure of F of A to a folded final value A, then kata is going to return you a function that goes from the recursive F to the A. So you're not dealing with recursion anymore, you're dealing with non-recursions, zero recursions. Paramorphism is similar to kata, except for the fact that at every node, you have the history of the input to the previous computation. So that's going to be super useful. We are going to be using para. And histo is going to have all the history of the data computations that happened in the previous steps. We are not going to be using histo for this talk. This is kata, para, histo, same, except for the fact that my F was bifunctor. So you have a value V and A, V representing what's in the leaf node, A representing the recursion holes. And the reason for why I kept mentioning bifunctor is this is missing in many, many places. And I was kind of struggling with, I need to map both these values. And most of the times you have this functor instance in recursion scheme. And when I was searching through some of the papers, they were actually discussing about bifunctor, so which makes sense. Kata, not going into the implementation of kata, there are so many talks around that. Kata, as I mentioned, if you know how to go from F of A to A, right? It doesn't matter what that V is, you know how to go from a recursive F to A. Okay, so why? Tracing was actually pushing some attributes into the children, right? Pushing the stack into the children from the parents. So, but then that's not tracing. Like it can be bottom up too. Like it can be top down or it can be bottom up. So, because you know the entire information bottom up as well. All you need to do then is to pass that down back again to the leaf node. This leads us to the terminologies in attribute grammar. It's good to have some kind of formalization here so that you can refer to different magical implementations in the attribute grammar side of recursion schemes, and you can blindly copy paste that into the Scala code to get some fun. So the attribute algebra or attribute grammar kind of represents both inherited value, something the children got from the parents, and also the synthesized value the parent got from the children, which is the bottom up. And the tracing can make use of both synthesized and inherited values and make it available in the leaf node. What that means is we dealt with f of a to a. Now we are going to deal with f of a, but just that a is a function. A function, f of a function to a function. So you're folding to a function. And that's it. Like you're folding, you're making use of catamorphism, but you're folding it to a function. So just for explanation purpose, I'm going to have a kata that just folding stuff to a function. This is just for better visibility or understanding. Essentially, you can simply make use of this kata itself. Everything is compiler-driven code base. These two implementations are exactly the same. Now I'm going to build one method that goes into our non-recursive observ, pattern match on these case sum and build this algebra. What was that, our algebra? That's f of a function to a function. And that function is going to return a recursive ops, very similar to anamorphism, but it is folding to a function that returns your recursive structure back again with the extra piece of information at the leaf node. So that's like kind of a machinery looking like, but this thing is compiler driven. Like I literally didn't think much except for satisfying the compiler. And then you're passing that algebra into kata trace. Remember, kata trace is not going from f of a to a. Instead, it is going from f of a function to a function. So now you got a function in return after doing that much, and then you pass an initial value. I'll get back to B. Basically, that means as you push these inherited values, which got synthesized from the children back to the leaf, you need to keep applying some function. So for example, if I need a depth information, all I then need to do is trace. At every node, I need to keep adding the integer value, that is +1. I need to give an initial value, 0, and then pass the plan. So we got the depth information at every leaf node. All right. Okay. So if I can do all of this using kata, I can just simply copy paste all of this code with paramorphism, compiler driven code base. Just that para has got an extra history information at every node. So your new trace function will have an extra history method and satisfy the compiler, and then call paratrace. Going back to paratrace, I think I didn't mention about paratrace. It's not going from a function to a function. It's going from a history and function to a function. Once you get used to this logic, it's worth it. So that trace can be used for both depth information and also pass the trace information. Trace information is just keep adding the history to the list of recursive ops. So with depth and with trace are completely independent operations, just that ops has new information at the leaf node, and they are composable. So you can have with trace and with depth, and that's going to keep changing your program, which I find quite exciting every time I talk about this. So it's going to keep adding new things into the leaf node without hurting your original implementation. This is like a very dummy piece of our ops. And that's fair enough because our ops is polymorphic. It can be a query or it can be an integer value. And when we call the trace and depth together, at the leaf node, you have got the value, original value, like ratio of 20 versus 30 happened because you were calculating it as a part of a sum of a ratio and a right side value. And then you took the left side ratio, and then you ended up in the leaf value 20, which is going to be super useful when it comes to actually running a query against Postgres. That was a little bit of convolutions and fun together. I think I'll take another 5 minutes to finish this talk. Now we need to track some subcomputational result. That was another thing which I mentioned. So we dealt about fix, we know about fix, a very nice topic to explore. I need to annotate every node with the result value, right? That's all about subcomputation. And our result is a Z stream, and a Z stream is lazy. That's super cool. That's going to be super useful if you think about it. Annotating the values always dealt with this compose data type, in many talks and in many papers. So compose is basically f of g of a, and if my f is a tuple which is partially applied, then if my g is your non-recursive structure, then that means it's a tuple that has a result and the non-recursive structure, which is basically your subcomputation. Just that is your implementation of subcomputation. But then we are going to make that compose a little bit more ergonomic, and that's called as co-free. It's a co-monad. There's nothing that talks about co-monad here, but anyway, co-free is like the out-of-the-box structure available in the recursion scheme of things, where you can have a result type at every node, and that itself is recursive. So fix and co-free kind of play together. Fix, where each node annotated with some result R is co-free. So my annotated result is co-free of your non-recursive structure and R. Again, some machinery, but what's the value add? This is the second method that we are going to implement, which is going to open up lots of opportunities to build various things. We dealt with kata. Kata goes from fix to A, but we are now going to build kata CF. Many papers that I'm listing there, they are actually going to go into compose. I can't really explain what's the advantage of one over the other, but I've chosen co-free. Kata CF is going from fix to a co-free. Again, something very similar to anamorphism, which is unfolding, but then we are using kata. And the reason for that is, if you think about it, kata is a bottom-up logic, and that is what exactly that we need. Like, we need to finally come up with a final Z stream. We can't forget that. But while you build that, you need the subcomputational results. So it's definitely kata, but with extra piece of information. So that is called, as that method signature exactly shows, that you're folding over the original result to a co-free structure. Satisfying the compiler again. All I need is an algebra, which is f of co-free to co-free, because we are doing catamorphism to come up with a co-free. So you need to start with co-free, ending up with co-free. Satisfy the compiler and call kata again. Okay, so my simple result, like normal case, you have a compile method that compiles your execution plan to a final Z stream, pass it to the plan using kata, you get the final result Z stream. Cool. So how do I get the subcomputation result? Call the kata CF, which is our second method, pass the compile with a plan, and you get all the subcomputational results there. That's a subcomputational Z stream for leaf query 1, for leaf query 2, that's a second Z stream, and for the sum node, that's a third Z stream. Simply means that if you just put co-free.value, that's your final output. And if you care about the subcomputational result, you go deep inside and then fetch those values. That's really interesting that we didn't have too many data structures involved and we got the stuff done. And I called this thing a step. The kata CF method was taking a step. And that's because now you have the access to every node. So you don't need to do pattern match anymore. So for example, in order to bring in logging, it's quite easy because it's a step information. It's not the final fully computed pattern match. So that means with subcomputational result is kata CF, but with log is basically log.info, considering that is going to return a Z stream. And if you have the original compile method, I can take that FA and run that compile, resulting in a Z stream, and then do a pre-logging and post-logging and plan. So now you have got logging everywhere in your execution plan. Now I need to improve the performance. I need to come up with a performance node. Simple enough, because it's same as that of logging, just that you need to have a start time and an end time. And whenever you compile the final value, which is compile the original f of a, you again doing cat cf for all of this. Compile the original f of a, unzip fa. That's because catamorphism is f of a to a, so that it cannot go from f of a to b. So your final result is a tuple with the performance information in it. So you always want to start with the tuple, but then compile method doesn't take a tuple; it takes only a value, so you can unzip it. And then unzip for ops is quite simple as well. If you come back to this code and try and do things by yourself, you'll realize that. And do the execution time. So now you have the execution time at every node. If you take the value from the cofree, that's going to give you the final result. And if I map over the second type, I get the execution time at every node. Again, everything is on the same data structure. So you might be thinking there are so many code that we have written. Actually not. We have 2 case classes. I think I missed bifunctor type class too. So we are using one type class, which is bifunctor. So all that we had was, again, a summary of what I have done here is a real life example of a functionally designed code base resulted in an execution plan data structure represented by ops. And then we wanted to come up with an execution summary. For that, we used recursion scheme. And in recursion scheme, we had this 2 case classes and 3 methods. One is paramorphism, and the next is the paratrace attribute algebra that we have discussed. And then the final cata-CF, which is catamorphism, but folding into a cofree. With all of that, we have got top-down and bottom-up logic, everything in place with your execution plan. And these are some of the papers that and blogs that I have made use of to come up with some of those logic. I think that could be useful, and I'll make sure that I'm publishing this somewhere so that you can come back and refer to this. I hope some of it, at least some of it, is useful for every one of you. And that's all that I have for today.
Thank you so much. That was a fantastic talk, and you dropped some serious knowledge on us. I think we're going to have to do some symposia after this to get everyone up to speed on all the concepts you introduced there. But thank you so much for that.